Hi everybody, welcome back to AP Chemistry. This is Chapter 4, Lesson 9. And yesterday, at the end of our lesson, we talked about assigning oxidation numbers to elements because really to determine if something is reduced or oxidized, if its charge goes down or charge goes up, you need to know the charges. So the first thing I want to practice is just assigning charges and walking through that. So when you are given something to assign the oxidation state or charge to, you want to go through those rules we talked about in order yesterday. So anybody by themselves always has an oxidation state of 0 unless they tell you otherwise. So if we go through our examples here, and I think it's easier if we just call this example 1, 2, 3, 4, 5, and 6. Br is by itself. It is not in a compound, therefore its oxidation state is 0. And potassium is by itself, but they gave you an oxidation state. It says plus, which means its oxidation state is +1, okay? So those are the only ones there where they're by themselves. So everybody else works when they're in compounds. So you go through the rules in order. So for number 3, you go through your rules. Is there anybody from group 1? There is. Lithium's in group 1, so its oxidation state is always +1. Is there anybody in group 2? No. Is there any fluorine? Yes. Fluorine is always -1 in compounds. And so we've gone through our rules. We've assigned the oxidation states for everybody in that compound. Again, go through your rules for carbon dioxide. Is there anybody in group 1? No. Is there anybody in group 2? No. Is there any fluorine? No. Is there any hydrogen? No. Is there any oxygen? Yes. If I've said no to all the other rules, then oxygen is -2. And we can, of course, find carbon's oxidation state because all compounds are neutral. So since this is not a polyatomic ion, its charges will equal 0. There are 2 oxygens that are each -2, so the oxidation state of carbon is +4. Again, very similar to what we did with naming. Number 5 is interesting because this is a polyatomic. So instead of all the charges totaling 0, in this one, all the charges will total -2, the charge on the polyatomic ion. So still you go through your rules. Anybody in group 1? No. Group 2? No. Fluorine? No. Hydrogen? No. Oxygen? Yep. And when you've said no to all the other rules, oxygen is -2. There are 4 things that are each -2, so the total negative charge is -8. Now, instead of them equaling 0, remember I want them to add up to -2. So sulfur has to be then +6. The oxidation state is always given per atom, so if they ask me the oxidation state of oxygen in sulfate, I would say -2. I would not say -8. It's always per atom, okay? And then finally, the last one here, we have Na2O2. Is there anybody from group 1? Yes, indeed there is. There's sodium, and it's +1. Is there anybody from group 2? No. Fluorine? No. Hydrogen? No. Oxygen? Yes. Now, normally, if we said no to all the other rules, oxygen would be -2, but we said yes. We said there's somebody from group 1. So we can figure out oxygen based on sodium because all compounds are neutral. So you have 2 things that are +1, so the total due to sodium is +2. Which would mean the total due to oxygen has to be -2, but there are 2 oxygens to share that. So you'll have to divide that by 2, and the oxidation state per oxygen is going to be -1. This is an example of a peroxide, where the oxidation state is -1. So being able to assign oxidation states is the key to knowing who's oxidized and who's reduced. Oxidation is when the charge goes up in a reaction. Reduction is when the charge goes down. And if you look at this example, carbon on the left is -4, but carbon on the right is +4. So the charge has gone up, so we would say that carbon in methane is oxidized. Oxygen is by itself, so its charge is 0. On the right, its charge is -2. Its charge has gone down, so oxygen here is reduced. So you can identify who's oxidized and who's reduced once you assign the charges. We would say also that CH4 is the reducing agent. and O2 is the oxidizing agent. They'll use the language both ways. So I think you have a couple in your notes here. And this is the first one you have in your notes. We have a reaction, and they want us to identify who's oxidized and reduced, and who's the reducing and oxidizing agents. So the first thing you need to do is assign the charges. Because remember, if the charge goes up, then you are oxidized and known as the reducing agent. If the charge goes down, you are reduced and you are considered the oxidizing agent. So I'll go through my rules and assign the charges. Is there anyone by themselves not in a compound? Of course there is. Aluminum's by itself here, so its charge is 0. Iodine's by itself here, so its charge is 0. Is there anybody in group 1? No, in compounds. Anybody in group 2 in compounds? Nope. Any fluorine? Nope. Any hydrogen? Nope. Any oxygen? Nope. So then their oxidation states are simply what they are, what you've memorized them to be when they are stable ions. So aluminum's oxidation state when it's a stable ion is +3. Iodine's oxidation state is -1. Remember, oxidation state is per atom or ion, not overall. So once we know that, we take a look at what's going on in this equation. So on the left, aluminum is 0, and on the right, aluminum is +3. So aluminum's charge is going up, so it is getting oxidized and is the reducing agent. Iodine's charge on the left is 0, and it's going to -1. Its charge is going down. Therefore, this iodine is getting reduced, and it is the oxidizing agent. Okay? So if they ask you who's oxidized, who's reduced, you need to assign the charges, and that will allow you to tell who's oxidized and who's reduced. Here is another example. Okay? Go through your rules. Is there anyone by themselves? Sure there is. And again, you may want to pause and see if you can assign the charges yourself. So oxygen's by itself, its charge is 0. I'll write it up top because I like it up top better. Anybody in group 1? Nope. Anybody in group 2? Nope. Any fluorine? Nope. Any hydrogen? Nope. Any oxygen? Yes. And I said no to all the other compound rules, so oxygen in a compound then is going to be -2. Since I know that, I can figure out sulfur's oxidation state in here because there are two things that are -2, so that's -4, so sulfur has to be +4. I can figure out lead's oxidation state here because oxygen's -2, so that has to be +2 to make them equal 0. Everybody else can be determined through their normal charge as ions. Sulfur, when it's with a metal, is going to gain 2 to be a stable configuration. So it will have a -2 charge, which means our lead has to be +2. So to identify who's oxidized, I look for whose charge is going up. Now Pb is interesting because it's +2 on the left and +2 on the right. So it's very similar. Nothing's happening to it. It's not gaining electrons. It's not losing electrons. It's sort of like a spectator in this reaction. So nothing's happening to it. Sulfur is going from -2 on the left to +4. That's going up the number line. So sulfur is oxidized, and that compound is known as the reducing agent. And oxygen's going from, 0 down to -2. So oxygen's getting reduced, and it's the oxidizing agent. Notice, nothing is happening to the products. If I were to label these, I would label this compound is getting oxidized, and it's the reducing agent, and this compound is reduced, and it's the oxidizing agent. Nothing happens to these. They are simply what you have when the reaction is over. okay? Nothing specifically happens to those. All right, that's it for tonight. Happy Halloween, everybody. We'll see you bright and early tomorrow morning. Bye-bye.